Good morning, everyone. Welcome to the plenary session of the Wednesday CEDAR Workshop. At the beginning of the session, I would like to just remind you a couple of things. The most important thing is due to some technical issues of the room links, all of the individual workshop sessions have been updated. So if you have downloaded the older version of the agenda, please make sure to update them. And you can find the updated agenda on the CEDAR website, your email, or Slack. Just please make sure to use the correct link. So all the participants who have just entered the session, you are muted by default, and please submit your questions to Slido. The Zoom chat here will not be moderated. Please also make sure to rename yourself with your first and your last name, and so we know who the participants are. And also finally, this session is being recorded. So our first speaker will be Ingrid Knudsen from British Antarctic Survey, and this is a science highlight talk. She will talk about the simulated trends in ionosphere, thermosphere climate due to predicted main magnetic field change from 2015 to 2065.
Thank you very much for the introduction. And let me see if I can get this full screen. Yes. Okay, yes. And thank you very much to the organizers as well for inviting me to give this talk to you today. This is all based on a paper that I published together with Astrid Maute last year. Okay, so a few pointers on why we might care about the climate in the thermosphere and ionosphere. One practical reason is that we have a growing amount of space debris in near-Earth space, and including in the upper atmosphere. And the lifetime of that space debris is dependent on the upper atmosphere density. So it's very important to understand how long-term changes, what kind of long-term changes in upper atmosphere density might be expected in order to manage that space debris problem effectively. Another reason is that remote sensing signals pass through the ionosphere and can be distorted by the ionosphere. So also any long-term changes in the ionosphere could have practical consequences, for instance, for the stability of long-term measurements with remote sensing. And then the third reason is that there might be some connections to lower atmosphere climate as well. So for instance, we know that the stratosphere can affect the climate near the surface. And while it's more uncertain for sure if that applies also to higher altitudes in the atmosphere, possibly processes occurring within the thermosphere and an ionosphere might eventually have some bearing on what happens close to the surface as well. So various practical reasons. There are a number of different drivers of upper atmosphere climate change or climate variations. So very prominent in the upper atmosphere is, of course, the effect of the solar cycle and also geomagnetic activity variations that roughly track the solar cycle, but with a bit more fluctuations in there. But underneath these sort of approximately 11-year cycles is also longer term changes. So when I say long term, I typically mean several decades or so. That's what you typically understand by the climate. Another important driver is the increase in CO2 concentration. So in the lower atmosphere, CO2 of course warms the atmosphere, but in the upper atmosphere, it actually has a cooling effect, which causes contraction of the upper atmosphere. And that thermal contraction also means that ionospheric layers move downwards. And if you are looking at a fixed height in the thermosphere, you will see a reduction in density as a result of increasing CO2 concentration. And then there might also be some further changes occurring through changes in the lower boundary forcing as the atmosphere below responds to increases in CO2 concentration and also some other trace gases. And then the third important factor, which is what I will concentrate on, is the magnetic field. Magnetic field changes are continuously occurring, and they are especially important for the ionosphere. They are very regionally varying, so you will not see the same effect everywhere on the globe. In the figure here at the bottom, you see the magnetic field strength in 1950. This is the magnetic field intensity in the colors. And then this line, the white line here, is the magnetic equator. And the dots, the white dots, are the magnetic poles. And then this figure shows in percentage term, the difference between 2015 and 1950. So you see also the gray line and the gray squares here mark the new location of the magnetic equator and poles. So you see a northwestward movement and also a strong reduction here, especially in the main field strength, which is essentially an expansion and a westward movement of this region here, which is a region of already weak magnetic field known as the South Atlantic Anomaly region. So this is the region where we expect the largest effects of changes in the magnetic field to have occurred in the past, and actually also in the future. That is what we see. So a few years ago, a very interesting prediction of main magnetic field changes for the next century or so came out by Aubert, and here we have now the field of 2015, and based on that prediction, this is the difference between 2065, so 50 years into the future from 2015 and 2015 itself. These are absolute changes now. You see again a northwestward movement of main magnetic field structures, large changes here in main field intensity and movement here is the magnetic equator as well. This point here marked by the black triangle is Higamarka, and I will talk about that a little bit towards the end of the talk, because it's in quite an interesting location where you get large magnetic field changes, and of course it's an important observatory as well. So there are various ways in which the Earth's magnetic field can affect the ionosphere and thermosphere. So I've tried to give a bit of an overview here. First of all, a decrease in the field strength causes an increase in ionospheric conductivity, and that has important knock-on effects for the rest of the system. So on how much current can flow in the ionosphere, of course, but also it affects the Joule heating, which then impacts on the neutral atmosphere as well. Changes in magnetic field orientation are also very important because they cause changes in plasma transport processes, and especially the vertical component is very relevant, because if you transport plasma upwards, you move it into a region where there is fewer neutrals, so less recombination, which then increases the electron density. So you can change the electron density and the total electron content of the ionosphere by moving the plasma up or down. If you move it down into a region of more recombination, of course, the electron density goes down. Then changes in the position of, for instance, the magnetic pole and the auroral oval are also having an effect, because that changes the geographic distribution or the geographic positioning of typical high latitude phenomena, high latitude current systems and Joule heating and so on. And similarly, a change in the position of the magnetic equator is also important, because that changes typical low latitude features, such as low latitude current systems and the equatorial ionization anomaly, which affects the electron density. Okay, so to look at how those magnetic field changes affect or expected to affect the thermosphere and ionosphere, I used simulations with the thermosphere, ionosphere, electrodynamics general circulation model, the TIE GCM. We ran this model at 2.5 degree by 2.5 degree resolution and a quarter scale height, and performed 2 full year simulations with the magnetic field of 2015, labeled as MF 2015, and 2065, labeled as MF 2065. And basically all of those effects that I mentioned on the previous slide, so effects on conductivity and electrodynamics and mapping changes and so on, they are all included by this model. The only thing that is not really included is any changes that might arise from changes in how the terrestrial system interacts with the solar wind and the magnetosphere. So solar wind, magnetosphere, ionosphere coupling might be changed by changes in the Earth's magnetic field as well. But we have assumed a high latitude forcing driven by the observed solar and geomagnetic forcing for 2015 in both simulations. And so the only effect that is included is here an effect of changes in mapping. So the high latitude forcing is fixed in magnetic coordinates, but how it maps to geographic coordinates would be affected by the main magnetic field epoch specified in the simulation. Okay, and then we have hourly data available for both these simulations, and we analyze the average differences between the 2 simulations. So here are some results. This is a plot of the neutral density difference between the 2 simulations as a function of height. The black here is for all of the data. The solid line is a global average. The dashed is for the Northern Hemisphere only, and the dotted is for the Southern Hemisphere. And then the different colors are for high geomagnetic activity only, so data selected with a KP of more than 4, and the blue is for relatively quiet geomagnetic conditions. And the solid lines, or the thick lines, I should say, are statistically significant differences. The thin lines are not actually statistically significant. In the same way here, this is a table with joule heating power. This is for 2015. This is the differences, and in the differences, again, only the bold printed numbers are actually statistically significant. And so what we see is a slight increase in the neutral density as a result of main magnetic field changes, but it really is a very small effect, at most 2% change over a period of 50 years. So this is a really small effect, which comes from a slight increase in joule heating, mainly in the Southern Hemisphere, which is where we see the largest decrease in main field strength. And that decrease causes an increase in conductivity and causes an increase in joule heating. But it's a very small effect, as I said. Then for the ionosphere, we're looking at the total electron content here. This is again a global average to start with, but broken down by month and UT. This left panel shows the difference between the 2 simulations in absolute units, in TEC units, and in percentage terms here on the right. You see, for the most part, an increase in TEC, but there's a band here, roughly around 18 UT or so, where the TEC is decreasing, and the numbers, the changes are relatively small if you're looking at global averages, just a few percent or up to half a TEC unit or so. So that seems very small, but it's actually because there is a huge amount of spatial variation in these responses. So that's what I want to show next. So these are maps now for 2 different UTs. So we have 6 UT here at the top, 18 UT here at the bottom. On the left is for 2015, and then on the right is the difference between the 2 simulations. And what you see is that the largest differences occur wherever it is daytime. So at 6 UT, it's around 120 degrees east, which is where you have the largest TEC values. And then at 18 UT, it's daytime in this sector, and this is where we see large changes. Now, of course, the changes in this sector are generally much larger because this is an area where the magnetic field has changed much more than over here, for example. And also we can see now why in the global average, things sort of balance out here. So there's not much change at all. And it's just, overall, it's slightly positive. Here, there is also some balancing between negative and positive changes in TEC, but it just tips the other way where you get an overall slight decrease in TEC. But the absolute numbers are actually quite large here. So we have changes on the order of almost up to 10 TEC units, which is about 35% or so. So those changes are much, much bigger if you look at it locally. Then you might ask how much of this response, this figure here, or the two panels here at the top are the same as what I just showed. You might ask how much of this response is due to changes in the mapping between geographic and magnetic coordinates. So you can't completely separate that because you have actually got processes that operate in, or processes that are best organized in geographic coordinates, and other processes that are actually more organized in magnetic coordinates, but they interact with each other. So you can never completely separate out a mapping effect, but we attempted to do that by plotting the results instead of as geographic longitude here as a function of magnetic longitude. So you remove some of that mapping effect, and you do see a more concentrated response here over a smaller geographic region. So some of what you see here clearly is to do with changes in the mapping between geographic and geomagnetic coordinates. In physical terms, what causes the TEC response, we found that it's mostly to do with changes in vertical transport. So we see here 3 different vertical transport terms. The top panel is the vertical E cross B drift. Then we have the vertical movement that arises from horizontal winds that push plasma up or down magnetic field lines. And then the bottom panel is the vertical component of diffusion along the magnetic field. So again, we have here 2015. This is the difference between these 2 simulations. And this pattern here, I should say, we had large values here, but because the magnetic field is almost vertical, that isn't really having as much of an effect as these low latitude changes here. And this pattern here is somewhat similar to what we see in the changes in TEC, and also what goes on at other UTs. So this is all at 18 UT, but what actually goes on before also has an impact on the TEC changes that we see at 18 UT. So we think that mostly it's the vertical E cross B drift that contributes to these changes in TEC, but other transport processes have some effects as well, as you can see in the other panels. Then a few results for Jicamarca here. So this is the electron density profile at Jicamarca. We have 2015 here in the black and 2065 in the red. So you see an increase in the electron density at this location. And if we plot this, if we plot the peak electron density, so NMF2 as a function of local time, then you can see that it's mainly a daytime phenomena that extends somewhat into the evening and the night as well. And so we wanted to check if that is indeed caused by changes in vertical E cross B drift. And we do indeed see changes in vertical E cross B drift that precede the changes in NMF2. Initially, we thought this seems the wrong way around, because we actually get a reduction in the vertical E cross B drift, a reduction in the upward E cross B drift, I should say. So at first, I thought that that wasn't actually explaining the result here, because a reduction in vertical upward E cross B drift should reduce the plasma density. But then we have to remember that Jicamarca is in a very special location close to the magnetic equator. And in fact, if we look here, this is now the NMF2 as a function of latitude, which shows the equatorial ionization anomaly region. So we have the trough here, right at the location of Higgamarca, which is indicated by the dotted line. So Higgamarca is right in the trough there. And then it does move slightly into the crest region for 2065. So that explains some of the increase, some of the reason behind the increase in electron density, but also the entire EIA structure, and this is in the longitude sector of Higgamarca, is actually weakening. And that is, of course, completely consistent with a reduced E cross B drift, because it's the E cross B drifts that are responsible for this structure. So that was quite nice.
You have 2 minutes left.
Okay, perfect. So I'm at my summary and conclusions. I just want to highlight a few small points. So we have a very small increase in the thermosphere, which is actually too small to be reliably detectable if you consider that 1 to 2% increase occurs over a period of 50 years. And it's really unimportant compared to the CO2 effect on the density. For the ionosphere, main magnetic field changes are important, and they should be observationally detectable, and they could make a significant contribution to long-term trends in TEC in the future. But you have to be very careful about how you average both in time and in space. So that's all I have to say. Thank you very much.
Thank you, Ingrid. That was a great talk. There are a couple of questions on Slido.
Okay.
The first one is, how is the magnetic field in 2065 predicted, and what physics behind it?
Okay, so that's not my own work. It's based on this study by Aubert that I mentioned. I'm struggling to remember the details of that now, but I think what he did was, I think it was several forward model simulations, but what exactly is in his model, I couldn't tell you. And he performed some statistical analysis, I think, on that to come up with the best prediction, if I remember correctly.
This is a great example of the collaboration between space physics and the geoscience. The other question is, what high latitude driver is used for year 2065 simulation?
Okay, so it's exactly the same as for 2015. Both used the solar and geomagnetic forcing for 2015. It's just specified in magnetic coordinates, so it would change in geographic coordinates just because of a change in the mapping, but that is all that's different.
Thank you. The next question is from Shenrong, and he asked, can you comment on any observed signatures of the ionosphere and the thermosphere long-term changes potentially related to the circular changes in the Earth's magnetic field? Or are those trends still too weak to be detected, even in specific regions?
Yeah, this is a difficult one, because it's kind of hard to figure out, what changes could be due to the main field or could be due to other effects that operate at the same time. And Shunrong and I have looked at this before in some of his data and found that some of the trends in ion temperature at Millstone Hill might be able to might be showing some effect of changes in the Earth's magnetic field as well, but it wasn't really enough to explain all of the trends. And I think it's very likely that even in regions where the magnetic field is leaving a signature, there will still be a signature from other effects as well, such as the increase in CO2 concentration and potentially underlying solar or geomagnetic effects as well. So it's quite hard to separate that out. I think that is still, an area that is being worked on at the moment. I don't have really a definite answer to that.
Yeah. So the next question is from Ana Elian from Argentina. The main magnetic field considered is from IGRF with all its non-dipolar components, or just the dipolar part? And if is it possible with TIEGCM to consider a non-dipolar field For example, assuming a quadrupolar field during a polarity transition.
Right. So the first part is, yes, it is including the non-dipolar components in the IGRF, not just the dipolar components. I think that running the tight ECM with a quadrupolar field might be problematic because there could be assumptions in there, and I think there are assumptions in there that the field is roughly dipolar, and so it's okay if there are some deviations from it. But if the main structure is really quadrupolar, I'm not sure that that would work.
Okay. Now it's already 10:25. I think we need to move on to the next speaker. Thank you, Ingrid. There are a couple of more questions on Slido, and if you got a chance, please respond.
Yeah.
Thank you, Ingrid. Our next speaker will be Martin Zindak from NASA Langley, and this is a CEDAR Prize Lecture. The CEDAR Prize Lecture was established back in 1989 and which honors a recent outstanding science contribution of importance to the CEDAR community. So today, Marty will tell us in his discovery about the energy balance and the long-term change in the upper mesosphere and the lower thermosphere.
Okay, thank you very much. Can you hear me?
Yes, we can.
Great, thank you. Thank you for that introduction, and thank you, Ingrid, for setting the stage for a lot of what I'm going to talk about today in some more detail. Before I get into the talk, I'd like to give some acknowledgement and also dedication. I'd like to thank the workshop organizing committee for the invitation to give this talk. It's a real privilege for me, and I greatly appreciate that. And then a few colleagues I've worked with whose work will be in this talk one way or the other, Linda Hunt, Jia Yue, and Chris Mertens. I've worked with them for a long time, and very happy to have them as my colleagues and contributing to this talk. And the Sabre Science team, the Time Science team, of course, we've been together nearly 30 years now. Funding organizations in NASA Heliophysics Division and Earth Science Division. And then to thank Utah State and NASA Langley for building a great Sabre instrument, which I'll be talking about today. And then the long-term relationship I've had with NCAR, HAO, and ACD. And then finally, GNA Technical Software for getting all this great data out, not only for my use, but for the whole community to use over the last 20 years. And then finally, I'd like to dedicate the talk to all the students of science who are working so hard to advance our knowledge of the Earth system. And that's basically all of you in attendance today. So thank you for all that you're doing as well. So for introduction today, I'm going to begin with giving an overview of what I'll be talking about. We're going to have visits by some luminary scientists, Richard Feynman and Werner Sumi, and they'll make some comments throughout the talk as well. And then we'll go into talking about the role of CO2 in the climate of the mesosphere and lower thermosphere, and I'm going to abbreviate that by MLT since it's a bit of a mouthful throughout the talk. And then we'll talk about energy budgets, energy balance, and energy conservation. And then we'll get into the question of actually how does the MLT cool when carbon dioxide is added? And Ingrid alluded to the cooling already, and so we're going to actually get in and talk about how that actually occurs physically. And then towards the end of the talk, we're going to look at where the MLT is today and look at how much it's been cooling and contracting over the last 20 years or so. Then I'm going to give a summary and then a view to the future. So here's an observation about energy that Professor Feynman made in his book, 6 Easy Pieces. And he says, it's important to realize that in physics today, we have no knowledge of what energy is. But there's a factor, if you want to call it a law, that governs all natural phenomena that are known to date. There's no known exception, and it's exact as far as we know. And that law is called conservation of energy. And that's essentially the foundation for this talk today. And it's really the foundation for all of climate science. Climate science, whether it's the upper atmosphere, the troposphere, or whatever, is an exercise of applying conservation of energy and then trying to figure out how the system is changing based on that founding and that law, that phenomenon that to which we know no exception. And so whenever you see black text now throughout the talk, it's going to be Richard Feynman talking to us later on. And I always like to give a slide like this to kind of orient everyone to where I'm talking about today, because when I talk about mesosphere and lower thermosphere in different regions, people sometimes have different ideas or different thoughts about where that is, but I want to orient everyone. And so I've got this nice cartoon, and on the left-hand side, you see the the different layers of the atmosphere, the troposphere, stratosphere, mesosphere, and thermosphere, and they're defined by the general sense of the temperature gradient with altitude in those regions. And what I'm going to talk about today, I've got this "you are here," is the mesosphere and lower thermosphere, and I'm going to call that about from 45, 47 kilometers up to about 120 kilometers. That's the core region that I'll be talking about today, but I really want to emphasize that this region is not just a region unto itself. It really influences this entire geospace region from 45 up to, let's say, 1,000 kilometers. And this is the long-term change, again, that Ingrid alluded to. So we'll talk about this region, but keep in mind that it influences a much greater region other than what we'll be talking about today. Okay, so what makes the mesosphere and lower thermosphere interesting and worthy of study? There's been a lot of money spent in the last 20 years, actually 30 years, when you consider all the satellites that have been developed nationally and internationally that have measured this region. And so this is just some, it's not a complete list, but some of the fundamentals are, it's this what I consider a beautiful blend of photochemistry and aeronomy. You still have ozone as the main radiative drive in the mesosphere up to 90 kilometers, and we'll show that in a little while. It's one of the main heating mechanisms. But you have solar ultraviolet variability and particle precipitation influencing the thermal structure and composition. So you've got this blend of physics that you need to understand. And then, incredibly, almost atomic species start to become significant. As you get higher up in the mesosphere, density decreases, and as density decreases, you have longer lifetimes for atomic oxygen and atomic hydrogen. And this has a really remarkable influence on the energy budget of the 80 to 100 kilometer region. And we'll see that in a few minutes. And today we understand the MLT is now, it's really part of this complex ionosphere, thermosphere, mesosphere system. We call that the ITM system. It's really hard to talk about one of these, the ionosphere, without talking about the thermosphere and the mesosphere, or vice versa. You have to really consider all three of them, especially if you're going to have a model. You have to consider all of them at once. So it's a very complex system, and one with important societal consequences. And finally, we have climate change going on due to increasing CO2, and it influences the MLT, but as Ingrid alluded, it influences the entire perceptible atmosphere above it to the edge of space, and then may have impact on things like the space law, for instance, and how many satellites can be in a given orbit, deorbiting of space debris, and so forth. So it's very, very relevant scientifically and societally. So a lot of what I'm going to talk about today is going to refer to data that we have derived from the SABRE instrument on the NASA timed mission. SABRE stands, as you see on the header there, sounding of the atmosphere using broadband emission radiometry. And if you look at the right-hand side, you see the computer-aided design or the CAD drawing of the instrument, and you get an idea of its size and its mass. It's about 1 meter tall and about 3/4 of a meter front to back. It's 75 kilograms. It consumes 77 watts of power, but has a very modest 4 kilobits per second data rate. And it's on the time satellite. We've been up nearly 20 years now, and SABRE's operated, it has one mode basically, it's on all the time, taking data all the time. And it views the Earth's limb from 400 kilometers down to the Earth's surface, and it measures infrared radiance in 10 channels, 10 distinct channels from 1.27 to 16 microns. And from that, we derive over 30 data products, including temperature, constituents like ozone, water vapor, CO2, and very pertinent to this talk, rates of radiative heating and cooling. And we'll talk a lot more about those in just a little bit. One of the reasons for SABRE was the energetics of the MLT region, and that's why I'll be talking about here today. And the good news is we're approved at least through September 2023 in NASA's current operating plan, so we can look forward to at least 2 more years of data, and we really will get 2 full solar cycles in that time, at least. Okay, so let's dig a bit more into the talk, and I want to start with what I call the hypothesis of climate change science, and it was put forth here by the individual you see, the professor you see there on the side, the picture of Werner Suomi. I did my master's under Professor Suomi at University of Wisconsin in the mid-'80s, and Professor Suomi is the progenitor of all we do in satellite meteorology and satellite remote sensing today. It was he who invented the geostationary satellite for looking at weather, and so basically his comment was, the satellite doesn't move anymore, but we can watch the weather move. So anytime you see on your computer or on the television pictures of clouds moving and so forth, that's all originated with Werner Suomi at the University of Wisconsin back in the 1960s. And so he was one of the principals in 1979 in the first National Academy report that addressed the role of carbon dioxide in climate. And in the preface to that report, he had the following statement, which I have here up on the screen. He said, "For more than a century, we've been aware that changes in the composition of the atmosphere could affect its ability to trap the sun's energy for our benefit. And we now have incontrovertible evidence the atmosphere is indeed changing, that we ourselves contribute to that change. Atmospheric concentrations of carbon dioxide are steadily increasing, and these changes are linked with the use of fossil fuels and exploitation of the land." And then I highlight here in blue, this is the hypothesis of climate change science. Since carbon dioxide plays a significant role in the heat budget of the atmosphere, it's reasonable to assume or to suppose that continued increases would affect climate. Now, of course, he was talking about the troposphere, but this hypothesis is good throughout the entire atmosphere because changes in CO2 and increases affect the climate of the entire atmosphere. So we'll keep that in mind as we go forward. And when you see light blue text in the talk later on, it's going to be Professor Sumi coming back and talking to us. So what is the effect, what is carbon dioxide doing? We have two actual records right now measured in the atmosphere. The one on the left side, I'm sure all of you have seen. This is the NOAA record. It's sometimes called the Keeling curve. It's the atmospheric CO2 measured at the Mauna Loa Observatory in Hawaii, and it began back in 1958, coincidentally at the dawn of the space age. And there's two things you see with this. You see that CO2 is increasing, that's obvious. But if you're close enough, you will see that the slope of the black line is actually getting steeper. So not only is CO2 increasing, the rate of increase is increasing, and we're putting more and more CO2 in with time year over year. And then on the right-hand side is a really remarkable result from CEDAR. Jiayue has published this back in 2015 and updated since then. And at the very top of the figure, the black curve here is the Mauna Loa CO2 record. And then the pink and red and blue curves are the CO2 trends, the CO2 record derived from CEDAR at 80, 90, and 100 kilometers. And what we see is an increasing CO2 up in the mesosphere and lower thermosphere, and it's increasing essentially at the same rate that we see at the surface. So we know that CO2 is increasing in the surface and now throughout the entire atmosphere, and that the rate of CO2 is comparable in both locations. It's a really remarkable result that we now know, and we understand how CO2 is changing throughout the atmosphere. And so what is the consequence of the CO2 increase? Well, Ingrid referred to this as well. We have simultaneous, and the key word here is simultaneous surface warming and mesosphere and lower thermosphere cooling. On the left-hand side here is the observed surface warming from the NASA GISS record, and there are several of these. There's a group at University of California at Berkeley, a group in England at the Hadley Center, and then over in Japan, and pretty much everyone sees the same result, that over the last 100 and some years, the Earth's surface temperature is warming. And if you look closely at the figure from about 1960 on, we've had this steady warming. We've had a few hiatus, but overall the planet continues to warm. So up over here on the right-hand side, we have the record from CEDAR now, an 18 or 16-year record, looking at the trends. These are the trends in Kelvin per decade in temperature in the stratosphere, the mesosphere, and up to 95 kilometers. And the red curve here is the CEDAR-derived trend from about, I'd say about half a Kelvin to 0.7, 0.8 Kelvin per decade. And the black curve is the Wacom model trend, and they're within their uncertainties, they're within agreement. And so what we're seeing here is, again, the surface warming, but now through observation, satellite observation, we're seeing upper atmosphere cooling in the MLT. So that's the basis of what we're seeing, and now we want to go in and try to understand what's causing these changes more and how they come about. So I want to begin by stepping back and looking at the role of CO2 in the MLT energy budget, and then we'll talk about after that how it influences and how it cools the atmosphere. And so here we have some visit again from Werner Sumi. The light blue text are his words. So to understand the role of CO2 in the MLT climate, we must examine the heat budget of the MLT. And the energy or heat budget is an accounting of all known significant sources and sinks of energy. So we've got to really be accountants here. We have to take account of all the different terms, and I'll show these in a minute. There's a number of them. And we have to just add all these up in order to get the heat budget correct, and then be able to understand how CO2 is changing our atmosphere. But what we'll see is that CO2 does play a significant role in the heat budget, using Werner Sumi's words, and that it's therefore reasonable to suppose that continued increases would affect the MLT. And the way we examine the heat and energy budget is we're going to largely do this through the evaluation of radiative heating and cooling rates. And so what are these radiative heating and cooling rates? They're really derived, it's just an expression of the first law of thermodynamics. And the first law is just an expression of conservation of energy. And so I put that in black text here because it's Professor Feynman coming back and reminding us about conservation of energy and how that's important to what we're trying to do here, looking at long-term change. And so it's a relatively simple equation that we use. The left-hand side, dq dt, that's the energy gain or loss per unit volume, per unit time, and it's a function of altitude z. And we get a profile, basically, of this energy gain or loss. We either compute that or we compute it through our data. And that's equal to the density multiplied by the specific heat at constant pressure, and then by the heating or cooling rate, and that has units of Kelvin per day. And we get this profile. So I like to say it's a very simple equation. The right-hand side has three terms, one of which is a constant. And this is how we derive our heating and cooling rates in the atmosphere. I just want to give a simple example to illustrate how we do this for the absorption of solar radiation by molecular oxygen, for example, absorbing a Lyman alpha photon. And we simply write down dq dt is equal to this term here, these three terms. J is the photolysis rate. It's the rate at which molecular oxygen absorbs a Lyman alpha photon. Then that's multiplied by the molecular oxygen concentration and multiplied by the energy of that Lyman alpha photon. And then we equate that to the density in the atmosphere, which we know from our measurements, the heat capacity, and then we solve for dt dt to get the rate at which Lyman alpha photons here are warming the atmosphere. And we do that for all these different terms. And similarly for cooling with different equations, but it's the same principle that we use to get the heating and cooling rates. And we're going to use SABRE, and then we also have to, because we're worried about the solar terms, we need the solar spectrum from the source instrument to give us the solar spectrum so we can get all this information for the MLT. So what are the elements of the energy budget? And here's where I talk again about our accounting. We have a lot of terms we have to keep track of. It's kind of like your personal budget. You have income and you have expenses. So you want to keep track of all your income sources, and you want to keep track of all your expenses. Same sort of idea here, looking at energy in and energy out. For solar heating, ozone is very important. You have three bands, the Hartley, Huggins, and Chapuis bands. Oxygen absorbs across a large range of the electromagnetic spectrum. You have the atmospheric bands here, the AB and gamma bands, and the near infrared. And then you have Schumann-Runge, Lyman alpha, and Schumann-Runge bands, Schumann-Runge continuum. These span the ultraviolet and are critical in the upper mesosphere and lower thermosphere. And finally, even carbon dioxide in the infrared has some absorption that gives a weak heating, again, throughout most of the mesosphere and lower thermosphere. And then I said earlier on in the talk, I said that atomic species have an incredible impact on the heat budget of the atmosphere. And they do, because of this fact that we're up where density is low. Once you have something like O2 photolysis, it takes a lot of energy to photolyze an O2 molecule. It takes 5 electron volts. And so the energy when a UV photon dissociates O2, that energy goes away. It doesn't go away, it's not realized, and it's carried away by atomic oxygen in the form of chemical potential energy. And it's only realized then as heat when that atomic oxygen reacts or recombines with some other species in a reaction, typically or maybe far away from where the photon was deposited. So you have to have a detailed accounting of all the chemistry and the exothermic chemistry that goes on. And so there's 7 different chemical reactions that are important, and we have to keep track of all of these to get all of our energy inputs. And then finally, for the output, we have infrared cooling by carbon dioxide, ozone, and water vapor. But really, for much of what I'm going to talk about today, and particularly above 65 kilometers, it's almost all CO2, almost all infrared cooling by carbon dioxide. So we have easily over 30 terms of energy budget here, and we derive these again with SABRE and source data. So here's what solar heating rates look like, daily average in the mesosphere and lower thermosphere. And I'll just point out a few of them. Here's the ozone Hartley. We said early on that it's the main solar radiative drive, and here it is. It's up until about 90 kilometers. It's the main heating rate in the mesosphere and lower thermosphere. But then above 90 kilometers, the Schumann-Runge bands and the Schumann-Runge continuum and Lyman alpha become important. And here in the middle mesosphere, it's pretty interesting because you have the atmospheric bands, but you have these UV bands as well of ozone and O2, and they're all kind of comparable. So you have to do a really good job of calculating the heat budget here in these rates in order to get the energy correct, because it's several small terms, but all add up to be something significant. So that's what the heating and cooling rates look, I'm sorry, that's what the solar heating rates look like throughout the atmosphere from 50 to 100 kilometers. And the next thing we'd like to look at is the exothermic chemistry. And so back, well, you can see the date there. I'm dating myself here. 30 years ago, we had this startling prediction that the reaction that produces the hydroxyl molecule, the reaction of atomic hydrogen and ozone, by itself produced more heat in the mesopause region than all the solar radiation combined. And that was a striking result because that had not been computed that way before. But again, it makes sense because of all the energy that gets carried away by these atomic species in photolysis. They only can be realized through chemical reactions. And so this is what we had predicted, that exothermic chemical reactions would be the dominant source of heat in the mesopause region and would be important throughout the entire upper mesosphere and lower thermosphere. And so with CEDAR, what we've been able to do is tally up all those heating and all those heating rates, the solar and the chemical reactions. And this is the result we get. This is for 2007 global annual average solar heating and chemical heating. And what we find indeed from the CEDAR data is that chemical heating is the dominant mechanism by which the atmosphere between, let's say, 79, 80 kilometers and 100 kilometers is heated. It's heated through exothermic chemical reactions and solar radiation, but the exothermic chemical reactions are the dominant mechanism. And so that's a very good confirmation of that prediction that was made some time ago. Okay, so let's talk about the other side then. We talked about the heating, let's talk about the cooling by CO2. And so CO2 emission cools the mesosphere and lower thermosphere, and it does so by what we call vibration rotation bands. So CO2 is a triatomic molecule. It can vibrate, it's rotating, and it has a number of different bands, 9 of which in fact are important. It has a very complex vibrational structure, and you have these 9 bands which contribute to the radiative cooling, and these involve what we call fundamental bands, which are the first excited vibrational states, and then the hot bands, which are the second and third excited vibrational states. And so what you see over here in the figure is you see some numbers first at the bottom: 626, 636, 628, and 627 and 628. CO2 has a number of isotopes in the atmosphere, not only the molecule itself, but we have to be concerned about which isotope of CO2 is there. And by the different isotopes, we look at the whether it's got an extra neutron in the oxygen atom. Is it, for example, 628, you have oxygen 18, carbon 12, and oxygen 16 making up the molecule. 627 would be oxygen 17. 636 is a carbon isotope. And so all these are important, and remarkably so, because these minor isotopes, the 636, the 627, and 628, are less than 1% of the total CO2 amount, but they're still important in the energy budget. And this was a contribution Bob Dickinson made back about, well, 40 years ago with this discovery. It was quite surprising at the time, but it has held up, and we have to include all these. So what we do on CEDAR is we calculate with a very detailed radiative transfer model the radiative cooling rates for these 9 CO2 bands for every profile of temperature that we measure. And here's an example of what those rates look like for all these different bands. So again, you've got cooling rate on the x-axis, altitude on the y-axis, and all these different bands are important. I'll point out a couple things. The red band here, the red color, is the fundamental 626, the primary isotope fundamental band. But below 79, below 80 kilometers, let's say, the first hot band of CO2 is actually cooling the atmosphere more than the fundamental band is. So really remarkable. And then here you have an isotopic species, a 636 isotope fundamental band is important in cooling. And another thing I want to point out, we talk about CO2 cooling, and that's fine. The net effect is cooling, but actually some of these weak bands and isotopic bands actually are warming the mesosphere and lower thermosphere. So in order to get CO2 cooling right, you've got to include all these bands, and it's not because they're all cooling, but a handful of them are actually heating the atmosphere. And so we do this in great detail on Sabre, just like everything else, in order to bring together the entire energy budget. And so that's what we've done here, and that's what this figure shows right now. It's the global annual heating and cooling in 2004. All the other years look very similar to this. The magnitudes go back and forth with the solar cycle, but this is the fundamental result. The red curve on the left-hand side is all the total solar and chemical heating terms that I talked about added up. And then the blue curve is the CO2 radiative cooling. And the first thing we can remark is, again, using Professor Sumi's words, is that CO2 does indeed play a significant role in the heat budget of the mesosphere, because it is the one factor that balances all of the solar and chemical heating. And we see this near balance, and so we really can conclude that energy is conserved. Again, to use the advice of Professor Feynman, energy is conserved, and on the global annual scale. And I'm just amazed at this, because I know all these terms that go in, 30 or so, calculated all these different ways, and we add them all up and they come out looking this close. It's really remarkable. I would say that I don't have I don't have uncertainty bars on this, but these agree within their uncertainty in large part. I will make a comment though and say we do expect there to be other heat sources, turbulent dissipation, for example, in the upper mesosphere and lower thermosphere. And that is probably why we're seeing here that the total heating and solar chemical is actually less, because this is throughout the Sabre data. The total heating is always less than the radiative cooling. So I think it's a sign that we have a handle on the dynamical heating part of the mesosphere as well. But I won't go into that any further. But what I would like to talk about then is, okay, so we see here that CO2 is an important part of the energy budget. So how does increasing CO2 work to cool the atmosphere? Pretty much a very fundamental question. And again, so at the chart here, how does CO2 increasing actually cause the mesosphere? What's the physical mechanism by which CO2 causes this cooling? So I'm going to put up two options. This is the quiz for today. Option A, we know CO2 is increasing in the mesosphere and lower thermosphere. We know that from observation. And we know that CO2 works to cool the mesosphere through emission of infrared radiation. That's what we have just seen through going through the energy budget. So doesn't more CO2 mean more cooling, that is more infrared radiation, and then the mesosphere and lower thermosphere temperature decreases? Isn't that how it works? Or I'll give you option B. Well, we've seen though that the mesosphere and lower thermosphere has a decreasing temperature with time. That was the Garcia et al. Results from 2019. By fundamental infrared physics, objects emit less infrared radiation at lower temperatures. So this seems that won't a colder atmosphere have less infrared radiation as CO2 increases? These two options seem like they're opposites, and they are. And so, well, which of these options is correct? Does A or B describe how CO2 cools the mesosphere when it increases? Well, actually, neither of these is correct. And so the question is, well, why is that? And how then does CO2 cool the atmosphere? So let's talk a little bit then about infrared radiation and exiting the mesosphere and lower thermosphere. In general, infrared radiation is the exhaust of the climate system. Infrared radiation is expelling the energy that's deposited into the mesosphere and lower thermosphere system by the sun, by these chemical reactions, or by dynamics. The only way to change the energy coming out is to change the energy coming in. And on climate timescales, annual to decadal, the energy leaving the MLT has got to balance the energy coming into it. And again, here's Professor Feynman. Energy has to be conserved. So the MLT cannot be made to radiate more or less energy by changing its composition. And in the long term, if there's no long-term change to energy coming in, there's going to be no long-term change to the energy coming out from the MLT. So we've got this conundrum. How, though, we know it's cooling, we know there's more CO2 coming in, what's going on? And so we're going to come back to our heating and cooling rates, and we're going to use these now in reverse to compute the energy fluxes. And again, I put up the first law of thermodynamics, and again, here's Professor Feynman, energy conservation. And we're going to take our derived cooling rates in K per day, and then we're going to go back to the left, and we're going to calculate the dq dt and get these rates of energy deposition per unit time per unit area, per unit volume, and we're going to get those and get profiles of those. And then we integrate those with respect to pressure, or do a vertical integration. We're going to get the net flux of energy of infrared energy that exits the MLT. And that'll be in watts per meter squared. And then we're going to integrate that over the globe because, again, climate change and all this energy conservation really can only be considered in a global annual scale. And so we're going to look at this over the globe. So what we're really going to look at is the total radiated power in the infrared from the mesosphere over this 20-year record that we have with SABRE. So what does the satellite record show? And so on this figure here, you can look at the x-axis. This is from 2002 through 2020. And the red curve is the daily global power from all the bands of CO2 that I mentioned, all those 9 bands added together and integrated from 65 to 105 kilometers. And it's the total power in watts. The units are 10 to the 11th watts. If you work this out on a global average, it's about 42 milliwatts per square meter. But the red curve is 7,000 points. It's the entire SABRE record every day, global average. And what you're really seeing there in the red curve, you're seeing the weather of the mesosphere and lower thermosphere. And the blue curve is, because we're interested in climate here and long-term changes, we compute a 360-day centered running average, and we do that average and we step it one day, another 360, and we do that all the way through to get this blue curve that you see here, which all of a sudden doesn't have much variability in it. And if you kind of look hard, you can see there's kind of a solar cycle in there. And so already just doing this annual average, we've taken out all this weather of the mesosphere and lower thermosphere. And we've got this now, this climate-like average that we want to look at. And we want to ask the question, well, what's the long-term trend in this blue curve here, this climate average, if you will, of the energy, the infrared energy cooling that cools the mesosphere and lower thermosphere? Is there any long-term trend in energy in that? And so the answer is no, there is no long-term trend. Once we take that, I'm going to step back here. Once we take the blue curve here and we do a least squares fit of F10.7 to this blue curve, we remove the solar cycle because that's the varying part of the energy, at least externally, into the mesosphere and lower thermosphere. So when we remove that solar cycle part of it, and we look at different layers throughout the mesosphere and lower thermosphere between 60 and 85 kilometers, 80 to 93, and 93 to 100, there's still some variability there in the energy coming out, but there's essentially no trend in that in either of these 3 layers throughout the mesosphere and lower thermosphere. So this is all making good sense right now, at least to me right now, so far, that there's no trend in energy once we remove the variable part from the solar cycle. And so we're still left with this question. Well, then if there's no trend in energy, how is the mesosphere cooling over these 20 years? So let's go and let's get back into the physics. I think this might be the second equation that I've got in the talk today, because I really don't like putting equations in talks. Look over here at the cartoon, and this is just any layer in the atmosphere. And these arrows all indicate pencils of radiation. And it's these pencils of radiation that we use to compute via the radiative transfer equation. And we sum all those up to get these fluxes and powers and so forth. And if we just look, though, at the basic equation for what describes from a layer of atmosphere, what describes the emission from that layer, the radiance, and as a function of wavelength or frequency, because we have to do this monochromatically because the spectral variation is very great. The radiance exiting the atmosphere is given by this equation. I said the atmosphere. The radiance exiting a layer of atmosphere is equal to the emissivity of the layer multiplied by what we call the source function. The emissivity is a number between 0 and 1, and it is dependent on the CO2 amount. It's basically a spectroscopic term. The source function is kind of like the Planck function. It is in local thermodynamic equilibrium. The MLT is not, but for all intents and purposes, the source function still depends on temperature the same way the Planck function does. So in the long term, if the energy into the system is constant, then this energy output must be constant, which is what we've seen. And so what happens is that as we increase CO2, we increase the emissivity. But since R is constant, J has to decrease, that is, temperature has to decrease to keep R constant. So what happens in the mechanism by which CO2 cools the mesosphere and lower thermosphere is that adding CO2 allows the mesosphere and lower thermosphere to radiate the same amount of energy, but at a lower temperature. And this is how cooling of the mesosphere and lower thermosphere is accomplished. And it allows this constant no trend in energy after we remove the solar cycle to occur, and it allows the atmosphere to cool without having to try to expel more energy that's coming into it, for example. So, and I want to have a disclaimer here. Don't try this at home. This does not apply to the troposphere and to global warming. The physical setup and the physics is entirely different in the troposphere, and so this is not how this is not to be used as an explanation of how the troposphere cools. I'm sorry, how the troposphere warms due to increasing CO2. It's how the mesosphere and lower thermosphere cools. Okay, so we do have a cooling and contracting mesosphere and lower thermosphere. And let's say, well, how much is a cooling and contracting? What's the record? What does that look like? So here it is. This is the record observed by CEDAR. And again, since this is climate type quantities, we're going to look at global annual means. And this is from actually, this goes down to about 30 kilometers in the stratosphere, up to 105 kilometers. And this is the difference in the global annual mean temperature. And the blue curve is from 2002 to 2020. So the entire CEDAR record is 18 years. And you can see that the entire stratosphere, mesosphere, and lower thermosphere are dramatically cooler in 2020 than they were in 2002. This is largely because we have 2002 was near the beginning or near the peak of the solar cycle at that time. In 2020, we're just eking out of this solar minimum that we went through. And so it's really a solar maximum, solar minimum comparison. If you want to compare 2009 and 2020, and these are kind of like two solar minima periods, you still see for the most part that between 2009 and 2020, except for like right around here, around 90 kilometers or so, that the upper mesosphere and lower thermosphere is cooler in 2020 than it was in 2009. And so the large contribution to this cooling is the weakening solar cycles over the last 20 years, but also about a Kelvin, maybe a little bit more than a Kelvin of it, at least below 93 kilometers, is due to increasing CO2. So you've got these two effects going on. And this has really given a substantial effect on the structure, not just the temperature structure, but the entire thickness, if you will, of the MLT system. And we're going to take a quick look at that now. So we'll go on. And the way we look at the thickness and how the atmosphere is contracting as it cools, we look at the geopotential height. And we use the basic difference of geopotential, which is a gravitational potential energy per unit mass at altitude, at a given altitude h. And it's defined by the integral there. It's just the integral of the acceleration due to gravity with altitude. And the geopotential height is the geopotential defined there phi of h, but relative to the standard acceleration due to gravity at our surface. So it's phi divided by g0. And this is another CEDAR data product for every profile of temperature we make. And we register our temperature profiles in pressure. That is, pressure is CEDAR's vertical coordinate. And so each of those pressure and temperature profiles, we get a profile geopotential height, about 1,500 of those per day. And we can look at those then to see how the geopotential height changes of all these different pressure surfaces in the atmosphere. And that gives us then a measure of how the thickness of the different layers is changing. Just to show this a little bit more in a cartoon, again, pressure is the natural vertical coordinate of the atmosphere. It's also the natural vertical coordinate of the CEDAR data. And we compute the geopotential height between any two pressure surfaces at one time here, or one temperature, and then in a cooling atmosphere, as the atmosphere contracts, as it cools, we get the geopotential height at another time. And we see this decrease, and we see this thickness then, the difference between the geopotential heights changing and decreasing. And this will be observed over time in the mesosphere and lower thermosphere, and we'll see this. And it is really remarkable. And that's what we've got here in this figure, that CEDAR-derived change in geopotential thickness from 2002 in meters. The carry-away message is that the entire mesosphere and lower thermosphere has contracted from 2002 to 2020. And what we look at here is the change in thickness of the geopotential height relative to the 1 hectopascal surface. So this is like 47 kilometers for these 4 different pressure surfaces in the atmosphere. And so to make it a little bit easier, I put here on the side the approximate altitudes that we're looking at here from 47 to 105 kilometers over the 20 years of CEDAR record, or 18 years. You can see the solar cycle effect going down, coming back up, and then coming back down. But right now, the atmosphere between 47 and 105 kilometers is about 1,500 meters thinner than it was in 2002. Going from 47 to 93, it's about 700 meters thinner. 47 to 80, about 375, and then even 47 to 65, it's about 130 meters thinner. So we've seen this entire cooling of the entire mesosphere and lower thermosphere due to the cooling. Again, it's largely solar cycle driven, but it's also got a CO2 component in it. So I'll finish here with a summary and final words from both Professor Feynman and Professor Sumi. Energy is conserved, and CO2 plays a significant role in the MLT heat budget. And from observations, we've seen CO2 is increasing throughout the entire perceptible atmosphere. This is causing simultaneous surface warming and MLT cooling. And I should emphasize, this is an unusual, this is an expected result. This is a scientific method in action. For over 40 years, we have seen predictions of surface warming and upper atmosphere cooling, and now we're observing them and confirming those predictions. So it's a real triumph of the scientific method. So increasing CO2 then cools the MLT by allowing it to radiate the same amount of energy but at a lower temperature. Today, the MLT is 2 to 20 degrees colder than it was in 2002, and the MLT has contracted by over 1,500 meters between 47 and 105 kilometers in that time. These changes are due to a combination of weak solar activity and carbon dioxide increase. And also, I didn't go into this a whole lot, but today it's pretty good case that the MLT is probably the coldest it has been easily since the start of the industrial age 200 and some years ago. And possibly it's the coldest it's been in tens to hundreds of thousands of years because of the low CO2 amounts in prior millennia. So let me conclude here with a view to the future. We had a recent article in EOS, the newspaper of the American Geophysical Union.
5 minutes left, Maury.
Oh, great, I'm right on time, thank you. The link to it is there at the bottom. If you just get a copy of the slides, you can look at that. We're very concerned going forward that the MLT has been under continuous observation since 2002. Many observations have been made globally by 6, 7, 8 different satellites internationally. But there are no new missions or instruments right now in development to really continue. And when I say continue, I really mean to make long-term observations and build on this remarkable record so we can understand, as the page there says, what's going on in geospace. So a gap in observation seems unavoidable. And the thing is, continuity is really going to be essential to understand the ongoing change of this region because it does influence geospace, as Ingrid referred to, and as we referred to in this article. So I'd refer you all to this article to take a look at that. And I know we have a decadal survey coming up, and we'll certainly be putting papers in on this to try to find a way to get continuous observation so we can understand what's happening in geospace as time goes on. And so with that, thank you again, and thank you for the ability to be here today and to give this talk, and thank you for the privilege of being your colleague all these years.
Thank you, Marty, for this very nice review talk. And there are several questions on Slido. The first highly voted question is, on slide 26, the CO2 radiated power drops occasionally almost to zero. What does that mean?
That's a great question because I haven't had time to go through that. But so this is the, it's the net radiation leaving the thermosphere, I'm sorry, the mesosphere and lower thermosphere. So what that means, and since that's like occasionally on a daily basis, the thermal structure is adjusting itself so that there's almost no radiative heating or cooling in the atmosphere, and that's what's going on. So you could, and I've got to go back and verify that, but that has to be what's happening. You can get a thermal structure where there's very little radiative cooling, I should say, radiative cooling by CO2. It's not isothermal, but you can get that occurring. So I want to go back and take those days where it does drop to zero, take those temperature profiles out and run them through radiative transfer code and verify that that's what's happening. But that's my belief as to what's going on.
Thank you. And the next highly voted question is, actually on the last slide, you mentioned that you're worried about there is no new mission lined up for this area. And so the question is the dynamic mission going to help?
Okay, that's a good question. I don't know what the dynamic mission is going to be. My understanding is that NASA is trying to get and we'll be offering an AO later this year to have some part of the overall decadal mission that was defined as dynamic, but some part of that to go along with the geospace dynamics constellation mission. So I don't know what's going to happen there and if there would be something in there, but it would be great if we could, but what we need is we need more than 1 or 2 years of data. We need some way to get a long-term record to continue this, because the problem we run into is that we take data for 2 years and have a gap and take data for 2 years. Things like calibration come in, and it becomes very hard to tie these records together accurately. At a trend of 1 Kelvin per decade, let's say, and the calibration technologies that we currently use for these type of measurements, it'd be very easy for different instruments to be off by 1 Kelvin. And so we have, well, there's the instrument, there's the atmosphere. And so these are the sort of issues we have to address. And we talk about that in our article in EOS. And I am preparing a more detailed article about this to really point out all these issues of calibration. Bottom line is I don't know what dynamics is going to do. It's not been selected yet. I hope it will help. And I hope we also get longer term kind of perpetual observations for this.
Yeah, thank you. It would be very important for you to express those concerns and perhaps put them down as a white paper for the decadal. Yeah.
Yes. Mm-hmm.
Thank you. Then the next question is from Li Ying. The question is, does the way of adding CO2 cool, the MLT, emissivity versus temperature, apply to the thermosphere?
So it depends where you're talking about in the thermosphere. If you get up above about 120 kilometers or so, CO2 begins to lose its effect at directly radiatively cooling the atmosphere. And so the thermosphere above that, it cools by conduction down into that region, into what we call the heat sink region, between about 130 and 100 kilometers, where CO2 is very strongly cooling the thermosphere. And so as CO2 builds up and it becomes more efficient, it also makes a much more of a conduit so that the thermosphere itself can cool as well. So CO2 cooling does impact the thermospheric temperature structure, but not by direct radiation, but by making the thermosphere, by making a more efficient conduit of that through conduction down into the heat sink region in the lower thermosphere where CO2 can radiate that. I may have jumbled that up too much, but that's the best way I can explain it right now.
Mm-hmm. Yeah, due to the time limit, let's take just one more question.
Okay.
The 2020 to 2009 plot shows a rapid drop off above about 100 kilometer. Can you comment on the uncertainty?
So that's a good question. So the uncertainty in terms of measurement, we have looked at SABRE's stability, and SABRE looks to be a very stable instrument on the order of a few tenths of a Kelvin per decade in temperature. And so that large change that we see up there, I don't think is due to anything in terms of temperature. I'm sorry, in terms of an instrument. I don't think it's an instrument effect. The rapid drop off, it could be due to several things. If it's an instrument issue in the algorithm, it could be, for example, the CO2. This is we did not use the combined temperature and CO2 retrieval. This is a standard SABRE data product where we put in a model CO2. Although I think it's pretty close. I don't think that would be it, but I'm just putting that out there. No, for some reason the mesosphere, the lower thermosphere there was looking a lot cooler and going much faster. So the only other suspect I would say right now is it's somewhere in the solar heating is dropping off, and we would have to look at that in more detail and see.
Thank you very much, Marty. And
Okay.
We need to move on to the next speaker.
Thank you.
So our next speaker will be Brandon Jones from NSF, and the topic will be education and diversity programs at NSF.
Hello, can you hear me?
Yes, we can.
Okay, great. Thank you so much for the invitation. I got to catch a little bit of Marty's talk there, so it's always good to be able to hear the latest science, especially in the Earth system sciences. But we're going to switch gears here a little bit and discuss, as was mentioned, education and broadening participation programs at the National Science Foundation, mainly in the Directorate for Geosciences. And so I'm going to share my screen and pull up my slides here. Okay. Can you see that? Is that good?
Yes, we can.
Okay, thank you. There's an acronym that's been making its way across many organizations, academic, nonprofit, professional societies, and throughout the agencies. And it's beyond the traditional diversity and inclusion statements. As you see here at NSF, we've been using Be a Jedi, which it touches on obvious cinematic themes, but it means much more. So the belonging and accessibility is where we would like to be, and within STEM, we could say broadly. And the way to get there is through the Jedi concepts of justice, equity, diversity, and inclusion. So for this talk today, I'm going to briefly go through just a framing of where we are in the geosciences and what we think about as we are putting together programs and connecting with the community, like here at CEDAR, and working across agencies with our other colleagues. And then we'll talk about a couple of programs at NSF that is focusing on the broadening participation, again, mainly in the Earth system sciences, or what we call the geosciences. So the three main issues or take-home messages for you today, why Be a Jedi is such an important topic, is because the STEM workforce cannot operate at full capacity. And this is, you could take this as ecological principles. Organisms have to be in optimal zones where they're receiving everything they need from the environment in order to operate efficiently. And if an organism is stressed, then obviously they're not operating efficiently, and then they're not going to be able to contribute to the community and to the larger ecosystem in a proper way. And this is the same with individuals, with human beings who are scientists, who are scholars, who are students, who are moving through the system, because science doesn't conduct itself, humans do it. So we want to make sure the environments, research environments, vessels, field facilities, wherever, are welcoming for those individuals. Secondly, individuals who are in the workforce cannot operate, as I just mentioned, at full capacity if they're stressed, and therefore that hinders their productivity and also then impacts the overall enterprise. And the third, there are planets facing all hands on deck problems, but all hands are not on deck. They have not been on deck, and even some that are on deck are not, again, able to be fully involved or fully themselves for different reasons. And I just mentioned this, and this is the main reason that the broadening participation programs at NSF exist, because there is a recognition that just as important as intellectual merit is, broader impacts or the societal relevance or the human dimension of science is just as important, which is why those criteria at NSF are key for every proposal that comes in. If we take a look at the very successful play Hamilton, and those that have seen it know, and those that haven't, there's a scene where there's a song with a chorus line, I guess you could say, that says, "Immigrants, we get the job done." And that's the notion of the United States from the very beginning, that you come here from another country for better opportunities, and you come through the right way, and you move into society, and you're afforded the benefits, and you take advantage of education and training and job opportunities, and et cetera, et cetera. But the issue with some of us in the country is that we were never immigrants. Okay, so some of you are familiar with that acronym there, BIPOC. If you have not heard that, it means Black, Indigenous, People of Color. And so it refers to Native and Indigenous peoples, refers to those of Hispanic ethnicity, mainly in this instance, of Mexican origin or Puerto Rican origin, and of course, those that are referred to as Black Americans or African Americans. None of those groups of individuals were immigrants, okay? Native and indigenous were already on the land, as was descendants of Mexican, or ancestors of Mexican and Puerto Rican communities. And of course, for Black Americans, their ancestors were brought over here forcefully and then forced into slavery. So there wasn't an immigrant issue with them. More so was it involuntarily being incorporated into the United States. And it just so happens that we still, after almost a half a century of programs on diversity and recruitment and getting students in from these groups into the sciences, in ocean, atmospheric, polar, and solid earth sciences, we still have an issue with retention because, may I offer, that the emphasis was on recruitment. The emphasis was on increasing the numbers of individuals from these groups, but there was never too much effort on the environment that these individuals were being recruited into. Mentoring was a part of that, but even the mentorship training and the mentoring skill building for those individuals, like faculty, like graduate students or postdocs or whoever happened to be in leadership positions for the students coming in, maybe they didn't have everything they needed. And so there's this retention issue. And because we still have the mindset of let's recruit and we'll bring them into programs, we'll bring them into departments or agencies or universities or REUs or what have you. And where I had a great experience, I came through an REU, I came through this program, I went through this institution and this university, and I did great. I had a wonderful time, great lab mates, great experience, et cetera. And that's how we package our programs and present them to individuals when we're trying to recruit them. But time and time and time and time again, we see that individuals, and there have been groups of individuals, cohorts within some of these programs who did not have the experiences that we presented to them that we thought they could have. And why is that? And I would again argue it's not the individual that was the issue, it was the environment that they were brought into. It was much of field work in our geosciences or earth and space sciences is in isolated areas. There is a nuanced community within the given disciplines in earth system sciences. There's a nuanced community in science itself. And so for individuals that have not been a part of that for a considerable amount of time or are very new to that, we have to recognize that that's a social problem. That's not a science problem. It's not the science. The science is fine. The way science, for the most part, is conducted, that's not the issue. The issue is it's a human issue, put it that way. And because it's a human issue, we need experts who know about humans, put it that way. Our social and behavioral and economic scientists, colleagues have to be part of the discussions for designing of these programs and evaluation of these programs and sustainability of these programs, if we're really serious about moving beyond recruitment, moving beyond retention, and actually having environments, lab environments, vessel environments, field environments, any research environment and learning environment that's going to allow these individuals that are moving in to be their full selves, to give whatever it is to science and to receive whatever it is from science. So just as a way of a picture, because that always helps, we focused on fixing the participants. Oh, they need more education here. They need more training there. They need more experience here. If we could just get them fixed, they'll be okay. Again, 50 years of this, especially in the earth system sciences, hasn't worked. So when are we as scientists going to say, and I'm a marine scientist, which is why I'm using this this particular diagram, when are we going to say, okay, it's not the larvae that are coming into the bay, the bay is hypoxic. the bay is polluted, or what have you. We can run with the analogy, but we want to make sure that we are focusing on all aspects of this system, and so we're not just easily blaming one part or even the individuals themselves. So that's kind of the framing and the setup to some of the programs that exist at NSF, and especially in the Directorate for Geosciences, where I sit, for education and training for students, and also opportunities for early career faculty, et cetera. So one of our mainstay programs for entry and research experiences outside of REUs for students and early career scholars that are coming into the geosciences is called GeoPaths. And you see the title there, Pathways in the Earth, Ocean, Polar, and Atmospheric and Geospace Sciences, which covers each of the divisions within the Directorate for Geosciences, which some of you are familiar. There are 3 tracks within this program you see listed there in blue. The Informal Networks track focuses on research experiences in the geosciences in informal settings, and not-for-profit organizations are eligible to be the lead. So this includes museums, aquaria, learning centers, et cetera, professional societies. They can be the lead organizations in submission of proposals to this particular track. And if you, we can get the latest solicitation out to you so that you can kind of go over all the details there if you happen to be interested. The second track is the UP track, which is undergraduate preparation. This track, as it says, is focused on late high school, early undergraduates and their experiences with the geosciences. And we recognize that Earth system sciences often is not taught at the K through 12 level. It's usually chemistry, biology, and physics. We know that. There may be an environmental science course or AP environmental science, which is not adequate as far as geoscience content in most cases. And so this track is an opportunity to connect students to geoscience concepts prior to getting to a university or college, or even when they're newly admitted into one. So they broaden their particular or their possible science opportunities. You also see there in the red for the UP track that R1 institutions are not eligible to be the leads. They are eligible to be collaborators, but there's an understanding that those institutions probably should already have the support mechanisms and resources in place to support undergraduates. So this is a reason that they're restricted here. The graduate opportunities track is for graduate students, mainly those currently in graduate programs or transitioning into the workplace, or from undergraduate into graduate programs. And again, a focus on service learning and workplace skill building within the context of the geosciences is certainly an emphasis in the whole GeoPaths program. We do need reviewers. So if you're interested, please reach out to me. I'll ask the organizers if they could share my email with anyone who's interested. If you would like to be a reviewer for this program, we're always looking for people who have an interest in this topic. Other opportunities for undergraduates. I'm sure many of you are familiar with REUs, Research Experiences for Undergrads. This is where institutions apply to be an REU site, and then they recruit students from other institutions to come work with faculty, have research experiences over the course of the summer. Of course, with the pandemic, many of our REU sites, a few of them shut down, but many of them had the innovative capability to move to all virtual, which is really cool. So now as things are opening back up, we have these hybrid models where there's in-person and virtual, which is going to allow for greater recruitment and greater connectivity across the country for students who may not be able to travel for many different reasons. So this is great. You see some statistics here for the sites and the supplements that we have provided. And REU supplements are always, if you happen to be an REU institution, supplements are always available to you, of course, given the budget. But when we're talking about the diversity of REU students at sites that are running geo-related programs, we see for the atmospheric, solid earth, and ocean, the number or the diversity of students at these sites has increased over the years. And we are excited about seeing that trend continue. And as I mentioned with the pandemic and now lots of hybrid models, hopefully that will expand even more. We have the flagship fellowship program for graduate students. I don't really need to spend a lot of time here, but you know about the Graduate Research Fellowship Program, GRFP. And we have a lot of high percentage over the last couple of years, a relatively high percentage of first generation and underrepresented applicants. The numbers really are still low. So we're figuring out ways, having discussions here at NSF to outreach to minority serving institutions like tribal colleges, HBCUs, even two-year colleges, where there might be some interest but not awareness. And so we'd be interested to hear from the community on maybe ideas you have for dissemination of this kind of information, or better ways that NSF can communicate these kind of opportunities. We also have the intern program. You see this acronym here. And the intern program is about 4 years old, and it's a foundation-wide program here at NSF. And it's to support non-academic internship opportunities for graduate students. So really any award from any program at NSF can be supplemented with an intern supplement, which is separate than the regular supplement that projects receive. So it doesn't count against that regular research supplement that any project would submit for. This is in addition to. And so again, it supports graduate students who have an interest in possibly pursuing a non-academic career, which we've seen over the last maybe 10, 15 years. The majority of PhD students coming out of the sciences are not going into academia, but we still have an academic traditional training system that is training them to do that. So the intern program offers an opportunity for them to gain experience at professional societies or federal agencies or national labs or et cetera, any non-academic entity, to kind of try that out for 6 months and be supported for that. And so I would encourage you, if you're interested in that, to reach out to your managing PO for your project if you are a PI, and get some more information about that for your graduate students if they're interested. We also have within the Directorate for Geosciences postdoctoral scholarships. We have them in 3 of our divisions. I don't know if there's one for Office of Polar Programs, but in atmospheric, earth sciences, and ocean divisions, they all have their own separate postdoctoral fellowship or scholarship programs. So I would encourage you, if you're interested, or if you're a postdoc and you're just now hearing about this, to reach out to those individuals on the postdoc fellowship site, that contact information, to get more information about the fellowship. The biology directorate as well as the engineering directorate have some huge programs related to postdocs. So we are looking to supporting postdocs. We're looking to support even more in the geosciences. So we're encouraging people to apply, and we're trying to get that information out. As far as Be a Jedi programs or broadening participation programs, and I'm kind of leading into the last of the slides, we have the GOLD program that was started back in 2016 here at NSF. It stands for Geoscience Opportunities for Leadership in Diversity. And it was all about building the capacity for broadening participation in the geosciences, but it was not student focused, okay? The GOLD program was focused on, as I mentioned earlier in the earlier slides, on the environment. It was focused on the individuals that were already in the environment, professors, mainly professors, advisors, et cetera, chairs, deans, whomever, who had an interest in broadening participation, but maybe didn't have the skills and needed the trainings, et cetera, to make the environments better and more welcoming and more belonging, or increase the sense of belonging. And so from that Gold pilot program, we had 5 projects that came out of that, and these are the 5 themes of each of those projects. And so we had great success from those 5 projects, and from those 5 projects, that allowed us to move forward last year with a Dear Colleague letter and begin to look at expanding the Gold program, expanding the network, and so now it's called Golden, okay? And so from the DCL last year, we requested supplements to the original 5, or not requested, but offered supplements to the original 5 projects from Gold. But we also offered workshops, research coordination networks, and eager proposals, which are those exploratory, high risk, high reward proposals. And from that Dear Colleague letter last year, 2020, we received 20 something projects. We made 18 awards. Half of those were the exploratory innovative. And then we had a breakdown of the other types here. But as I move into the closing slide, I wanted to highlight those 9 innovative projects, the eagers. Here are the institutions in the far right column. And here are the themes that were pulled out of those eager proposals that these specific projects are emphasizing. So we see, for instance, mentorship is a main emphasis in most of the projects. And we see some focus on scholars with disabilities and some focus on race and ethnicity. And then there are some that focus on institutional policies, like at Oklahoma and Boise State, as it relates to tenure and promotion for faculty that are involved in broadening participation activities, what it looks like for workload balance for women and faculty of color at institutions. And so what are those institutional policies that need to be adjusted, changed, removed, whatever it is, that are barriers and hurdles and hindering individuals from moving forward in their careers and bringing all that they can to the scientific enterprise. So we're excited about what's coming out of those projects, as they were just awarded last year. And
Brandon, you have 2 minutes.
Okay, thank you. I'm finishing right here. And so we had a new Dear Colleague letter out this summer, and it just finished, and we are processing those projects now. So those awards will be made later this summer. And just some information about broader impacts for PIs to consider, and I can share these slides so you can have this information for later perusal. And that's it. So I'll stop sharing that.
Thank you, Brandon, for introducing us those various programs that's available from NSF to support, students at different career stage and also the early career postdocs. We got a few questions on the Slido. The first question is the statistics that you shown in one of your earlier slide reflecting the PhDs in the NSF JL section?
I believe you're referring to the paper by Bernard and Cooper-Dock. That was yes, it was graduate degrees in the geosciences by race and ethnicity. And what it was showing was that there's been a steady increase of master's and PhD degrees among white graduate recipients, but for the last 40 plus years, for all other race and ethnicity categories, that has remained flat, like below, like you could get down and just count individuals. That's how low the statistics are. And for Hispanic, African American, Asian American, and Native and Indigenous. I believe that's the stat you're talking about.
Thank you. The next question is by Dolores Knipp, and she asked, you reported the percentage of diversity for the RU program. Do we have information on how effective or retentive the geoscience RUs are?
That's a great question. I would have to defer to my colleagues who run the RU programs, as those RUs are specific to the divisions. And so that's a question I could take back to them, because they track all of that data, and they may have something to offer there.
Mm-hmm. The next question is by Jonathan Crow, and he asked, can we get some basic data on the percentage of geoscientists that understand basic concepts, such as what is white privilege, or how does system racism persist without the presence individual racists?
Yeah, that's a great question as well. I can share with the organizers some recent literature, and there's a lot that's booming coming out of the professional society publications like EOS. If you just search over the last year, you'll find a lot there. A lot of workshop and recordings from the national academies on this, as well as the resources that I'll share with the organizers on just literature from geoscientists and social scientists who have been working with the geoscientists.
Mm-hmm. Thank you. In one of the slides, you mentioned the GeoPass program, and you also mentioned that the GeoPass program cannot be awarded to R1 university, right? So the question is, does the GeoPass provide a collaborative platform for finding university partners? For example, the research university wants to collaborate with minority serving institutions.
Yeah, excellent question. Let me clarify again. Just one of the tracks restricts R1s from being lead institutions. So R1s can be lead institutions for the informal track or the graduate track, but they cannot be the lead for the undergraduate track. However, to this question, they can be collaborators, and it would be up to the PI team to describe how that outreach to a minority serving institution or another university to your college would occur, and what project and what activities for students would then be a result of that.
The last question we got is, you mentioned graduate opportunities that are only available to students in the US. Is there a possibility of future graduate opportunities for international students?
Yeah, that's a great question. So right now, the intern program is for any graduate student. There's no citizenship requirement, because if a student could be an international student, but again, yes, they're at a U.S. institution, because that's where the award is made, that's going to be supplemented for the internship. There have been similar questions, and I don't know the level of discussion at NSF with policy about support, expanding that support for international students. We do have opportunities for international collaborators and for institutions to collaborate with other international institutions, including with funding. And so that may allow for some flexibilities for some students, but you would have to do some research with the proposal guide for NSF, the PAPPG, on what those policies are.
Yeah, thank you very much, Brandon. Those are all the questions we have on Slido, and thank you for spending time with us this morning.
My pleasure. Thank you for the invitation.
And for all the other CEDAR participants, thank you very much for calling in the plenary session of the CEDAR this morning. And at the end, I just want to remind you that all of the Zoom links for the individual workshop have been updated. So please make sure to check the latest version of the agenda. You can also find the information on the Slack channel and in the email sent out through the CEDAR mail list. So see you in the other individual workshops.